Welcome to my YouTube channel. Forget everything you know about jets. Imagine a plane that can fly faster than most missiles, dodge radar like it's invisible, and strike before anyone even sees it coming. Sounds impossible? That's exactly what engineers built, and it's the jet that still keeps America awake at night. Visual, fast cut montage, jet blasting off, radar screens flickering, thermal camera showing heat trail. On paper, this jet shouldn't exist. Its design defies everything conventional aerodynamics predicts. Yet, decades later, it still haunts U.S. radar operators. Visual, grainy Cold War footage of the jet taking off, radar blips flickering. For 50 years, engineers have been stuck on one problem: how do you build a plane that's virtually invisible, while still being fast enough to outrun missiles? The Cold War wasn't just about nukes, it was about delivering them first. Both superpowers needed a jet that could penetrate enemy defenses without being detected. Stealth wasn't a luxury, it was survival. Visual, map showing U.S.-Soviet missile ranges, overlay of radar coverage. The U.S. poured billions into radar networks. To beat that, you need two things: a low radar cross-section and supersonic speed. But these two often conflict. Visual, side-by-side of sleek stealth shapes versus delta wings for speed. Making a plane stealthy means smooth, rounded surfaces. Making it fast means sharp, thin wings. The laws of physics are not negotiable. Here's the fundamental problem: radar reflection and aerodynamics are at odds. Metal reflects radar. So does your wing shape. To reduce radar cross-section, you want flat panels at specific angles, but these panels increase drag, which slows the plane. Visual, 3D model showing radar waves bouncing off different shapes. And speed isn't just about pushing the throttle. At Mach 2, air friction generates temperatures exceeding 300 degrees Celsius. Materials expand, stresses spike, and the boundary layer, the thin air layer hugging the fuselage, can separate, causing instability. Visual, simulation of heat map along a supersonic wing. Solve one problem incorrectly, and the plane either melts, stalls, or becomes a radar beacon. Engineers turn to a combination of shape, materials, and stealth coatings. The jet you see here, pause for effect, is the MiG-25's rumored successor. Visual, 3D CAD reconstruction highlighting edges, wing sweep, tail fins. It uses a razor-thin delta wing for supersonic speed, but its fuselage is coated with radar-absorbent composites. Engine air intakes are carefully shielded to hide the compressor blades, the part radar loves to see most. Visual, exploded view of intake, showing shielding and composite layers. Even its sensors and weapons are tucked inside internal bays. No protrusions. Every inch is a compromise between invisibility and performance. The engines? Turbofans designed to minimize infrared signature. Hot exhaust is a missile magnet, so they mix ambient air to cool it down, like a jet version of stealth frosting. Visual, thermal camera overlay of exhaust plume versus standard jet. Nothing comes free. The materials make it incredibly expensive to build, millions per square meter of radar-absorbent composites. The thin wings make it unstable at low speeds, requiring fly-by-wire systems. And yes, it burns fuel like it's going out of style. Mach 3 capability comes with the efficiency of a gas-guzzling sports car. Visual, graph comparing fuel consumption and radar cross-section versus conventional jets. Stealth isn't invisible, it's just invisible until it's too late. One wrong radar angle or heat signature, and detection is inevitable. So why does America still fear it? Because the combination of speed, altitude, and stealth is still extremely rare. Even with modern radars and satellites, a jet like this can cross a continent before anyone fully knows it's there. Visual, animation of jet evading radar, reaching target. Economically, it's a nightmare. Each unit costs tens of millions, and maintenance is constant. It's not a mass production plane, it's a strategic ace. But here's the takeaway: human ingenuity pushes against the unyielding laws of physics. Every curve, every coating, every turbine blade is a battle between what's possible and what nature allows. And sometimes, that battle produces technology that even the most advanced military cannot ignore. Visual, slow pan of the jet disappearing into clouds, dramatic fade out. The jet that America still fears is proof. When engineers face impossible constraints, sometimes physics bends just enough to create legends. Curiosity doesn't need borders. And sometimes, it builds planes that defy them.